Rsync is a file synchronization and file transfer program for Unix-like systems that minimizes network data transferred by using a form of delta encoding called the Rsync algorithm. Rsync can compress the data transferred further using zlib compression, and SSH or stunnel can be used to encrypt the transfer. Rsync is typically used to synchronize files and directories between two different systems, one local and one remote. For example, if the command rsync local file user at remote host, remote file is run, Rsync will use SSH to connect as user to remote host. Once connected, it will invoke another copy of Rsync on the remote host, and then the two programs will talk to each other over the connection, working together to determine what parts of the file are already on the remote host and don't need to be transferred over the connection. Rsync can also operate in daemon mode, where it listens by default on TCP port 873, serving files in the native Rsync protocol. Released under the GNU General Public License version 3 and widely used. History: Andrew Tridgell and Paul Macaras wrote the original Rsync. Tridgell discusses the design, implementation and performance of Rsync in chapters 3 through 5 of his PhD thesis in 1999. Rsync was first announced on June 19, 1996 and the first release of major version 3 was issued on March 1, 2008. Uses: Rsync originated as a replacement for RCP and SCP. As such, it has a similar syntax to its parent programs. Like its predecessors, it requires the specification of a source and of a destination. Either of them may be remote, but not both. Because of the flexibility, speed and scriptability of Rsync, it has become a standard Linux utility, included in all popular Linux distributions. It has been ported to Windows and Mac OS. Generic syntax: where src is the file or directory to copy from, and dest represents the file or directory to copy to. Rsync can synchronize Unix clients to a central Unix server using Rsync SSH and standard Unix accounts. It can be used in desktop environments, for example to efficiently synchronize files with a backup copy on an external hard drive. A scheduling utility such as cron can carry out tasks such as automated encrypted Rsync-based mirroring between multiple hosts and a central server. Examples: a command line to mirror FreeBSD might look like %rsync-avz, delete ftp4de.freebsd.org freebsd/freebsd/. The Apache HTTP server supports only Rsync for updating mirrors. Rsync-avz, delete, safe links rsync.apache.org Apache dist to mirror. The preferred way to mirror the PuTTY website to the current directory is to use Rsync. Rsync or Rsync, Rsync and orguk is a PuTTY website mirror / a way to mimic the capabilities of Time Machine, see also TIM. Date equals date plus %y %m %dt %h, %m, %s, date equals date plus %ft %t. Rsync AP, linked dist equals $home current to important files $home back $date, lnnfs $home back $date $home current. Algorithm, determining which files to send. By default Rsync determines which files differ between the sending and receiving systems by checking the modification time and size of each file. This method incurs hardly any I/O and CPU usage, but will miss files whose content, unusually, has changed without modification to size or timestamp. Rsync can perform a more comprehensive check via the checksum flag, forcing a full checksum comparison on every file present on both systems. Barring rare checksum collisions, this avoids the risk of missing changed files, but incurs reading of every file present on both systems and is thus much slower. Determining which parts of a file have changed. The Rsync utility uses an algorithm invented by Australian computer programmer Andrew Tridgell for efficiently transmitting a structure across a communications link when the receiving computer already has a similar, but not identical, version of the same structure. The recipient splits its copy of the file into fixed-size non-overlapping chunks and computes two checksums for each chunk, the MD5 hash, and a weaker rolling checksum. It sends these checksums to the sender. The sender computes the rolling checksum for every chunk of size S in its own version of the file, even overlapping chunks. This can be calculated efficiently because of a special property of the rolling checksum. If the rolling checksum of bytes n through n plus s1 is R, the rolling checksum of bytes n plus 1 through n plus s can be computed from R, byte n, and byte n plus s without having to examine the intervening bytes. Thus, if one had already calculated the rolling checksum of bytes 1. 25, one could calculate the rolling checksum of bytes 2. 26 solely from the previous checksum, byte 1, and byte 26. The rolling checksum used in Rsync is based on Mark Adler's Adler 32 checksum, which is used in zlib, and is itself based on Fletcher's checksum. The sender then compares its rolling checksums with the set sent by the recipient to determine if any matches exist. If they do, it verifies the match by computing the hash for the matching block and by comparing it with the hash for that block sent by the recipient. The sender then sends the recipient those parts of its file that did not match the recipient's blocks, along with information on where to merge these blocks into the recipient's version. This makes the copies identical. However, there is a small probability that differences between chunks in the sender and recipient are not detected, and thus remains uncorrected. This requires a simultaneous hash collision in MD5 and the rolling checksum. It is possible to generate MD5 collisions, and the rolling checksum is not cryptographically strong, but the chance for this to occur by accident is nevertheless extremely remote. With 128 bits from MD5 plus 32 bits from the rolling checksum, and assuming maximum entropy in these bits, the probability of a hash collision with this combined checksum is 128 plus 32, equals to a 160. The actual probability is a few times higher, since good checksums approach maximum output entropy but very rarely achieve it. If the sender's and recipient's versions of the file have many sections in common, the utility needs to transfer relatively little data to synchronize the files. Note that if usual data compression algorithms are used, files that are similar when uncompressed may be very different when compressed, and thus the entire file will need to be transferred. Local changes in uncompressed files yield global changes in compressed files. This is particularly an issue with mirroring of archive files, such as disk images and compressed tarballs, where often individual files change. Some compression programs, such as gzip, provide a special resyncable mode which allows these files to be efficiently resynced, by ensuring that local changes in the uncompressed file yield only local changes in the compressed file. While the Rsync algorithm forms the heart of the Rsync application that essentially optimizes transfers between two computers over TCP/IP, the Rsync application supports other key features that aid significantly in data transfers or backup. They include compression and decompression of data block by block using zlib at sending and receiving ends, and support for protocols such as SSH that enables encrypted transmission of compressed and efficient differential data using Rsync algorithm. Instead of SSH, stunnel can also be used to create an encrypted tunnel to secure the data transmitted. Variations. A utility called RDIFF uses the Rsync algorithm to generate delta files with the difference from file A to file B. The delta file can then be applied to file A, turning it into file B. Unlike diff, the process of creating a delta file has two steps. First, a signature file is created from file A, and then the signature and file B are used to create the delta file. Also, unlike diff, RDIFF works well with binary files. Using the library underlying RDIFF, Rsync, a utility called RDIFF Backup has been created, capable of maintaining a backup mirror of a file or directory either locally or remotely over the network, on another server. RDIFF Backup stores incremental RDIFF deltas with a backup, with which it is possible to recreate any backup point. The Rsync library used by a DIFF is an independent implementation of the Rsync algorithm. It does not use the Rsync network protocol and does not share any code with the Rsync application. The Rsync library is used by Dropbox, a DIFF backup, Duplicity, and other utilities. Duplicity is a variation on RDIFF backup that allows for backups without cooperation from the storage server, as with simple storage services like Amazon S3. It works by generating the hashes for each block in advance, encrypting them, and storing them on the server, then retrieving them when doing an incremental backup. The rest of the data is also stored encrypted for security purposes. Rsync is a utility to encrypt files in an Rsync-friendly fashion. The Rsync algorithm ensures that two almost identical files, when encrypted with Rsync and the same key, will produce almost identical encrypted files. This allows for the low overhead data transfer achieved by Rsync while providing encryption for secure transfer and storage of sensitive data in a remote location. An alternative to manually scripting Rsync is the GPL-licensed GUI program Backup PC, which performs automatic scheduled backups to Rsync servers. As of Mac OS X 10.5 and later, there is a special Euro extended attributes switch which allows retaining much of the HFS file metadata when syncing between two machines supporting this feature. This is achieved by transmitting the resource fork along with the data fork. Solutions using Rsync, see also. Remote differential compression, references. External links, official website, Rsync algorithm.